let's not do it that way. Okay, Stephen, are we good?
Yes.
Can we see both boards?
Yes.
Okay, we're having some technical difficulties this morning. All right, so I think you probably want to take out a separate sheet of paper so you can jot some stuff down. David, are you okay?
Yeah.
So I want you to jot some stuff down here. I think of all the units in the calculus course, if I asked the BC students last year which one was the hardest one, they did a little survey at the end of the year, and they unanimously, even after completing the entire Calculus BC curriculum, what they said was this unit was the hardest one. This is absolutely the hardest unit, at least that's what those people said. And who really knows for sure? And I think I tend to agree with them that this is the hard unit because there's just so many different ideas that you guys are responsible for absorbing in a really quick way. This next unit that we start on Monday, I think is really going to be a friendly kind of unit for all the friends. I think grades are going to go up significantly. This is, some of you, please God, please. Okay, this next unit is good, but before we close out on this unit, let's kind of like see where we've been. The whole overarching theme for this unit is it's all applications of the derivative. So like we've been taking derivatives for a long time now. Applications of derivatives. And the very first place that we went to was L'Hopital's rule. L'Hopital's rule is going to be on the test. It has to be on the test. And the thing that I want you to remember about L'Hopital's rule is don't use it all the time. You only get to use L'Hopital's rule if what? Lewis, if what?
If it's infinity over infinity or 0 over 0.
If, number one, you're working with a limit and you're getting infinity over infinity or 0 over 0, those two popular indeterminate forms. Now, if you see infinity over infinity or you see 0 over 0 in a limit problem, then what L'Hopital's rule says is derivative of the top, derivative of the bottom. This is not the new quotient rule. This is L'Hopital's rule that just says derivative of the top, derivative of the bottom. Everybody okay? Mm-hmm. Now, there are other indeterminate forms that we've run into, like infinity to the 0 power, infinity minus infinity, lots of different kinds of indeterminate forms, but L'Hopital's rule really handles these two forms nicely. With all the other ones, you have to do some work to get it into an infinity over infinity or a 0 over 0 form. Pretty much, these are the big things I wanted to make sure we're clear for L'Hopital. Okay, so that's L'Hopital. The mean value theorem is one of those named theorems, and whenever a theorem gets a name, it's going to come up again and again and again. There are conditions that have to be true in order for the mean value theorem to apply. Specifically, what are they? Let's get some hands on this. What are the things that have to be true about the function in order to use the mean value theorem? One person, two people, 3, 4, 5, how long? Okay. The function has to be continuous on a closed interval is part of the condition. Lewis, what's the other part?
Differentiable on the open.
Differentiable on the open interval. Now those are the conditions that are true that you need for the mean value theorem. But the promise of the mean value theorem, what it gives you, Lewis, what does it give you?
There guarantees you a point C in between A and B.
Where something special happens. And the folks at the other campuses unfortunately can't see my beautiful poster of the mean value theorem unless Stephen does something with the camera. Right, but the mean value theorem says if you have a function that is continuous on the closed interval, differentiable on the open interval, then when I connect the endpoints of the interval with a secant line, if I find that secant line, there must be a place inside the interval, inside, not at the endpoints, where the slope of the tangent line equals the slope of the secant line. We're okay with the mean value theorem? Mm-hmm. Continuous on the closed interval, differentiable on the open interval. I'm giving Stephen all sorts of problems today. Sorry. That's the mean value theorem. Okay, number 3, absolute extrema. We started talking about absolute extrema, which means what? Which means what? Myra, what do we mean by absolute extrema? So keep it simple. Absolute extrema, absolute maximum means highest point, absolute minimum, lowest point. Is it possible for an absolute maximum to be a relative maximum?
Yes.
Right? Relative maximum just means you're doing this. Function changes increasing to decreasing. Derivative changes positive to negative. Is it possible for an absolute max to not be a relative max?
No. No. Because if it's an absolute max, it's a relative max. Yeah.
Oh gosh, I wish I had written that question on the test. What I just heard said was, if it's an absolute max, it must be a relative max. That is so false. That is so false. An absolute max does not have to be a relative max, and a relative max doesn't have to be an absolute max. And I've got 11 people who are staring at me like, what the heck did you just say?
I thought it was only about relative max. A relative max does not mean it's only an absolute max. For an absolute max, it normally has to be a relative max. It indicates the change.
Okay, that's not true. An absolute max has to satisfy one condition. There's only one condition that you have to satisfy to be an absolute max. It has to be the highest point. That's it. So for example, if I look at this function, I think a lot of you guys are stuck here. And you're like, this is a relative max and it's an absolute max. Okay? But what if the function does something like this? Now, where's the absolute max? Nope.
Well,
It's still there.
Where's the absolute max here?
Still there.
nowhere.
Where's the absolute maximum point, Andrew?
Nowhere.
Nowhere. Why?
Because you have arrows that keep on going.
I've got the arrows indicating that we're going up forever. There is no absolute maximum value here. However, what if my interval looks something like this? On this closed interval, where's the absolute maximum?
Top right.
Top right, like over here. This is an absolute max. This guy over here is a relative max. This is an absolute max that is not a relative maximum. Everybody okay? Now here's the thing. When you're looking for an absolute extrema, normally we look for a relative max first. We call that the candidate. And then we also check endpoints when there are endpoints. There were other ways to go about checking for absolute extrema. We would do like a number line test. And the thing to remember with the number line test, if your derivative changes sign just one time you change from positive to negative, then you have a relative max and an absolute max. Everybody okay? If there's only one relative extrema on the interval, right, think relative max. Oh, I went from increasing to decreasing and that's all the function does, then that relative max is an absolute max. But if there's another turning point, if there's a place where you have another relative extrema, here we have a relative minimum, then you have no guarantees that that relative max is actually the absolute max. There's no guarantee that the relative min is the absolute min when there are two turning points. You need one point, one extrema, one relative extrema, and then you know. All right, extreme value theorem, two conditions have to be true here.
Oh, it has to be,
Extreme value theorem, two conditions.
Continuous.
The function has to be continuous. The second thing that has to be true, it has to be on a closed interval. Okay? So another named theorem, here are my conditions, continuous on a closed interval. The promise, though, the thing you're guaranteed, is that if I have a continuous function on a closed interval, there will be an absolute maximum and there will be an absolute minimum. Where do we look? We look at our candidates and we look at the endpoints all of the time.
wait, is that the one where it can't be the endpoint?
No, it could be the endpoints.
Which one is that, mean value thing where it can't be the endpoint?
Mean value theorem cannot be the endpoints. Extreme value theorem could be endpoints. Good. Okay? Now optimization, oh boy. But you guys did really well on optimization. Optimization, it's just word problems, right? It's word problems where we're going to look for absolute max and absolute mins. The mistake I want you to avoid here is doing something like the number line test and saying, oh, I have the answer, I'm done. Or the mistake of, I found a derivative, I set the derivative equal to 0, I'm done. With optimization, when you find that candidate, you're at the halfway point. You then need to do like number line test and see where derivative is changing. Or if you have endpoints, you take that candidate and you plug it back into the original function with the endpoint. Lots of options, but getting to the candidate, you're like, yay, halfway. Implicit differentiation, we're almost done. Implicit differentiation, we're taking derivatives with respect to x. The big difference here, the big difference with implicit differentiation. How do you know you're doing implicit differentiation?
Two variables.
Oh, wait,
Such as x.
Well, there's usually two variables,
On the same time.
but it's two variables on the same side of the equation. Things like x squared plus y squared equals 6. Right, this is an implicitly defined curve because the x and the y are on the same side. Now I know all 11 of you and all the friends watching at home are smart enough that you could absolutely write this in explicit form. You could solve for y, but that's not the point. It is defined implicitly, and we're going to take the derivative. And the thing to pay attention to when you take the derivative of y, multiply by dy dx because of changing stuff. Okay? Okay, and then lastly, related rates, you're taking derivatives with respect to time. That's the big thing. Right, so like over here, the derivative would be 2x plus 2y dy dx is equal to 0. But if I was doing some problem over here, like volume equals pi r squared times the height, if the radius is changing with respect to time, if the height is changing with respect to time, then I take a derivative with respect to time. The derivative on the left with respect to time. dv over dt. Now I come to take the derivative on the right. 2 pi r squared h. Pi is a constant.
2 pi, oh,
2r
Okay, 2r
I'll put the 2 in the front.
dr over dt
times dr over dt
time
Times H.
times
times
dh.
dh dt.
No, times H. It's a product rule.
This is a product rule problem. You gotta be careful. So I want to back up. And I would maybe say, okay, I know I have product rule here, so what I need is pi times the derivative with respect to t of r squared times h, and now I'm just focusing in over here. The derivative of r squared, 2r dr dt times the h, plus r squared times the derivative of h, dh dt, and then we multiply by pi. Okay. This guy here is your constraint. This is the thing that's true all the time. If this is true all the time, then this is the thing that I'm going to go and take a derivative of. This is the kind of equation I'm going to come back to, right? And I might say, like, how's the volume changing at a particular radius? And you're like, oh my God, I don't know the height. Where am I going to get the height from? You normally go back to this initial constraint equation. Everybody okay? That's like it for me, like being all talky. So here's what I want to do. I wanted to give you guys the big picture overview, and now we're going to split the group up a little bit. I'm going to give you guys time to start working on some multiple choice questions. While you're working on the multiple choice questions, I'm going to grade the quiz that you took home last night. I'm only going to look at the multiple choice, and I'm going to look at the answer from the free response right now. Those of you that need more support, you're going to move to one side of the room with me. Those of you that are good, you're going to keep working on these multiple choice questions. So here are the problems I think you should work on. This is not getting picked up for a grade. These are just good practice problems. In the problem set packet, it's pages 27 to 31. We're officially done with the student packet. Problem set packet, pages 27 to 31. I just picked a mix of problems that made me say, those are really good questions. I want my teenagers working on these. 3, 4, 7, 8, 9, 11, 13, and 17. For the friends at North Central and East End, there's not really going to be much to watch for the next 15 minutes or so you might just want to work on these and see what you can do. Later on, as soon as class is over, I'm going to email worked out solutions to all these multiple choice questions and some practice free response questions to everybody at Southwest, East End, and North Central. My recommendation with this take-home test, spend some time this weekend working through these multiple choice questions and free response questions before you take the unit test. I'd maybe like block off an hour or more tomorrow. I know there's a lot going on. An hour or more tomorrow to study, and then on Sunday take the test. Okay? But you'll get the solutions. Okay. All right, enough for me. 3, 4, 7, 8, 9, 11, 13, 17. See what you guys can do for the next 15 minutes, and I'll regroup y'all in just a bit. I better check the times. Excuse me.
34 and Chevy.
Yes.
No, Charlotte.
Um,
No, Charlotte is there's some children.
what should I do with it for?
Who just said that?
For what?
But only for 10 minutes.
3?
Huh? Yeah, I mean, I'm gonna go into because some
How do you know it
people-
has a horizontal tension?
Because it goes up and then to go down.
The graph, okay.
Yeah.
You can.
Is the graph
Wait, wait.
as it go up and down?
Go for
I was like,
3 is
I know it's pretty good.
it's 10 over 3, which is 3.33.
wait.
Oh, I have a
Okay,
friend
I don't
over
even know
here
what
sitting right next to
Well,
me.
like, you just have to do,
Yes.
Like
I
auto?
was wondering how
Why?
someone's
because
story
you
was going to end.
do the,
It's gonna end with an end.
Oh, yeah, it ended.
If something has to.
All right, and Myra,
Why?
please fix my homework grade. I put in a 10?
Yes.
Okay. Well, work
You're
hard.
right, yeah.
We'll do better.
I'll change.
Don't let that happen again, okay?
I'll change to a 50.
Oh, I forgot there's the minimum.
If it-
Oh, yeah, I got
Why is it 3?
Grade, grade. Alright. By the magic of supreme preparation.
Yeah, it was something. It was like something crazy. And
Should, right?
it was like something.
Who's on C?
I'm still thinking about it.
Because it has to be continuous. Do we know if it's continuous on the person? You know.
Well, if it's different, well, then it's continuous. Yeah.
Oh, so then. Right.
No, it's not that kind of.
Yes.
it's close to
Okay.
We'll do that shit.
Wait,
Well, if it's not using C, are we all good with that?
The horizontal tangent was?
Because Montana's function is equal open interval. So.
Wait, what's-
Because there's gonna be a shape.
Power 4 is square root 2.
Because you know there's gonna
oh
be.
yeah, yeah, in the middle
It has to
one.
go up. It has to
3,
go up.
3, 4, 6.
But then I can
Negative
do
5, 4, 5.
Literally, if you draw it,
It was 3 per.
negative
But C
5.
was in
power 4
between.
Five.
sine of power 4 is also, I mean,
One has to be, we always say one.
And 3 has.
10 and 3 over 5. So it's 3 pi over 4.
Because,
That's root of 3 over 2.
okay, so then, why wouldn't there be a horizontal tangent?
You have the right idea, and now you have to just push. It's also a little bit
Cause that can't be.
You're saying it could be G for this person?
Yeah. I'm spooked.
It's not equal.
I didn't realize one.
I know. That's why I'm over here.
Do it at the end.
I will say.
Take it. Create it now.
Have you been ready?
Damn, I did good work. And you did really well in the free response. Andrew?
But I have the right answer to my work.
Are you handling? You are having all sorts of issues. You can't handle the camera. I say, Andrew, you look at me, you look at his grade. I mean,
So just pause stuff on.
nice. And did well in the free response. Stephen, you're also a super smarty. Nice job. You can stay. All right. See you later.
Each one has to be a number in between.
IVT is,
Why are you looking at the IVT?
She's supposed to know what
I
I
like the view, one of them.
Sorry about that. All right, Myra. No.
This one gets closer.
You get another 10.
And
Another
nice
10.
job in the free response.
But say, come here, broke up the
Free response.
There is,
I knew I got
there's
All right, Aaron, Palmo, and David. So Aaron, Palmo, and David, we're gonna go meet over there for free
You should
response.
be E, right?
Right now? Yep.
All of them.
The IVT says.
The IVT says if you have a function, a closed interval, and the value like this endpoint over here is the value of like 6, this value, endpoint is value of negative 4, all the y values in between 6 and negative 4, there'll be at least one place where that y value happens. Alright.
MVT means.
Alright, turning the camera because I don't want all this good stuff to be getting out. I'm going to put the camera back here. Steven, see how you like it. Okay, so we're just gonna, maybe you're having some good conversation that they're a part of. At the very least, we'll keep you focused and on task. Alright, friends over here. Okay. Hello, David, and Aaron, feel free to make comments on your own work, but in like a different pen color if you need it.
I just gotta finish.
Okay. Alright, so right now we're just focus on the free response.
Because I'm getting 0 at the top.
I feel like it's fine.
So what's happening in this situation? Two planes are getting closer to each other.
No, that'll be
And
one.
this is actually
So
0.
what are the things that we know for sure in this diagram?
Which is
There's a plane over here, there's a plane over here, and this is like collision point. Okay, so what do we know? Y is 200, is this the Y? Y is 200. And this guy over here is, Aaron, are you coming back?
Transing out for a minute.
So that's 150 miles, and this over here is 200 miles. So right now you're telling me how far apart they are from this collision point. What else do you know?
The one on the y-axis is traveling at
600 miles per hour on the y-axis. So how am I going to represent this 600 miles per hour? You're saying negative 600? Why negative 600? You're right. Tell me why. Right. The way that this plane is moving, it's getting closer to the collision point. So that means that that distance is decreasing. dy dt is negative 600. What's happening with plane x? So dx dt is negative 450 miles per hour for exactly the same reason. Are you guys all okay with this? Now here's the thing. There has to be an equation that pulls everything together. If you don't have an equation that pulls everything together, you can't take a derivative. So what's the thing that pulls everything together? Okay, I mean, I was hoping that with the diagram provided, the Pythagorean theorem might be on the brain. Okay? Okay. So we've got x squared plus y squared. Now the thing we've got to be careful about, these two planes are at different points coming closer to the collision point. So not only is this plane getting closer to the collision point, and this plane getting closer to the collision point, the distance between the two planes is changing as well. And so I need a new variable. It's not like the ladder where the ladder just slides down and stays the same length. So what I'm looking for is that relationship x squared plus y squared equals z squared. Now that you've got this thing that's true, this is what I'm going to take the derivative of. And so it should be 2x dx dt. And then 2y dy dt, 2z dz dt. Okay, what's the thing that we're actually looking for in this problem? Okay, we're looking for the rate at which this distance between them is getting closer. So what I'm looking for in a final answer is the dz dt. So when I come back over to this equation, what are the things that we know? We know x. Yeah.
Real quick, when I write this, do I put when they both like when one plane equals 150 miles and the second plane equals that?
So I would say, so you can just give me one of those things because when one of them is true, the other one is happening at the same time.
Is that number 7?
Right, this is the free response question, which for the most part you guys were all fine with. Okay. So I'm just going to go down the list. Do I know what x is? Yes. Do I know what dx dt is? Yes. Do I know what y is? Got it. dy dt? Got it. Do I know z? Right, I didn't give you z, but you're going to go back to the Pythagorean theorem to figure out what the z value is. Once you know what the z value is, you get dz dt right out of that. Okay, I'm going to go take a lap. I'll be right back. How are we doing over here? Okay, so what have we done so far? You found the derivative. Is the derivative cosine x over 2 times a half? Good. What else did you find? So here's with the mean value theorem, what you need is continuous differentiable function on the interval. The mean value theorem says if I find the slope of the secant line connecting the endpoints, there's going to have to be a place where inside the interval where the slope of the tangent line is the same as the slope of the secant line. That's what I'm looking for. Did you guys find the slope of the secant line? That's the problem. Okay. You're always going to have to find that slope of secant line to help move you forward. Because what you get here is your derivative equation. You set this equal to whatever the slope equation is. The slope of the secant. Yeah. Yeah.
Yep.
And then negative 4y plus 4x dy.
Negative 4. I did my math.
Yep.
Okay, I didn't have my calculator. That's why.
Okay.
I spaced out for a good 4 minutes.
Gotcha. All right. A popular question that lots of you guys struggled with was question number 3. I'm going to go over number 3 over here on the side if anybody's interested. Folks that missed number 3, this is not public shaming. Aaron, you might want to stay with me.
I am. I'm just helping them.
You are staying with me.
I'm helping
Giselle,
them.
you might want to come on over.
Okay.
Myra might want to come on over. Celeste might want to come on over.
Times.
For question number 3.
I got negative x.
Find if that equals first.
All right, Aaron, let me give you your quiz back.
Right.
Aaron,
Yes.
here you go.
Thank you.
All right, and we've got Carmen, Lewis, Andrew, Steven,
All this part.
Giselle,
All this.
I lay Myra, and when Celeste comes back, let's grab Celeste. Your friends are coming back.
Huh?
Three.
I don't remember.
Alright.
One is necessary.
And
Not but remember there's one.
call me psychic. I knew number 3 was going to be the right one.
Yeah, three is- one and three. Yeah.
Giselle,
I can do it.
Very good.
So like, see that there should be the x has to be greater in order to make it more constant. So you can calculate
why? Alright. And yeah, that's yours. Okay. If you want to continue writing on the quiz, feel free. Just use a different color so that I know what's yours and what's mine. Okay. So, is everybody clearly implicit differentiation? Like clearly implicit differentiation? And we know that because we got x's and y's mixed in together. You've got to take a derivative.
Why?
Okay. How do I take the derivative of this first?
E, the power of x, y,
Yeah.
times the derivative of x.
Okay, e to the xy times the derivative of xy. I cannot emphasize enough.
Answer.
Okay. If you guys can just freeze on the free response a little bit. Is everybody okay with the derivative is e to the xy times the derivative of the xy? We're doing a little chain rule. Celeste, you're going to want to join us for number 3. So e to the xy times the derivative. Right. The goal here is to just make your life a little bit easier so you're like, okay, I know what's going on here. I know how to handle this. Hi there. Okay, minus derivative of y squared. 2y dy dx equals derivative of e minus 4. 2 has to be 0. Yes, sir. What can I do for you?
Did you ask for more room or just like?
Did I ask for more desks?
Yeah.
No? No, we're great with desks. Thank you so much for checking up on me. And I think the locks got cut off the desk that had the locks because that was driving me nuts. Okay. But thanks for stopping by. Not done with the calculus because we actually haven't taken the derivative of the xy. Product rule. So I've got e to the xy, product rule, derivative of the first, that's going to be 1
Number three.
x times dy dx minus 2y dy dx is equal to 0. You've got to find dy dx when x equals a half and y is equal to 2. What we need some clever algebra. We need legal, clever algebra. Now you could plug in the 1/2 and the y equals 2 right now if you wanted to, if that makes life a little bit easier. Totally okay. Another option, you could like distribute the e to the xy through. So I'm gonna try it that way. So e to the xy times y plus e to the xy times x dy dx minus 2y dy dx is equal to 0. And the key here is any term that has the dy dx you want to keep on one side. Anything that doesn't have the dy dx you send over to the other side. And maybe we can do a couple of things here at the same time. Right, we've got 1, 2, 3 terms total. This guy doesn't have the dy dx, send it over to the other side. These two have the dy dx, what's going to happen here? If they both have the dy dx term. We're going to factor out the dy dx, and then after we factored out the dy dx, you're going to divide by all this stuff. Okay? So let's see. If I think about factoring out the dy dx, that's going to leave me x e to the xy minus 2y, and on the other side now I've got negative y e to the xy. dy dx, then we're going to divide. I know I'm totally in the way, I'm sorry. dy dx is just going to be this guy over here divided by all this stuff. So negative y e to the xy. In the denominator, x e to the xy minus 2y. And then from here, plug in a half for x, plug in 2 for y, and hopefully we're done. So I'm curious, like, what were the mistakes that were getting made with number 3?
Oh, I just didn't know how to factor out the DYDX. So
Okay.
I know how to.
Does that make sense now?
Mhm.
Just how you're feeling? Okay. Was everybody okay with the derivative part? So finding the derivative was good. And then usually with implicit differentiation, it's the algebra that's going to be a little bit of a pain. All right, we've got 13 minutes left, so we're going to bring everybody back together. Stephen, if you wouldn't mind moving the camera. And we're still in the problem set packet. Yes, we are. All right. So, friends at North Central, friends at East End, friends at Southwest, we're all friends, we're all coming together. I need to get all these quizzes back from people. So, I'm confused. Can you talk about that a little bit? I want to get started.
Very valuable question.
This guy here, I'll distribute it to the friends.
That was my mistake.
Wait, how about that? That's the thing, it's not on both sides.
All right. All right, friends. With this one, I'm going way old school. This is like from the AP College Board graveyard. This question's from 1985. Okay. All right. So we're on page 33. Not question. Yeah, question 5. Okay, balloon shown below is in the shape of a cylinder with hemispherical ends of the same radius as that of the cylinder. The balloon is being inflated at the rate of 261 pi cubic centimeters per minute. At the instant the radius of the cylinder is 3 centimeters, the volume of the balloon is 144 pi cubic centimeters, and the radius of the cylinder is increasing at a rate of 2 centimeters per minute. At this instant, what is the height of the cylinder? I want you to take 2 minutes on your own, read through this, translate all the stuff in this problem to calculus notation. If you can come up with the constraint equation that's going to bring everything together, go for that too. So, back in the day, back in 1985, the College Board was not giving out formulas. They were not being friendly with the problem whatsoever. They were, however, awarding points for can you just translate the stuff into some calculus notation. So let's get some hands on this, and then you're frozen for a little bit. Give me anything that you know for sure. After reading this problem, some calculus thing that you know. Palimon, give me something and you're frozen.
The radius is changing when the balloon 61 cubic meters.
Okay, so you're talking about the radius is changing. Specifically, how's the radius changing?
At a rate of 2 centimeters per minute.
Okay, now I want to be careful. You missed a really important word there. You skipped right over it. How is the radius changing?
Increasing.
The radius is increasing at a rate of 2 centimeters per minute. So what is that really? This is dr dt. So dr dt is 2 centimeters per minute. Polynomial, you're frozen for a little bit. Stephen, what you got for me?
dv over dt equals negative 261 pi centimeters.
dv over dt is equal to negative 261 pi cubic centimeters per minute. Where did that come from?
Wait, why is it
Oh wait, increase.
Right? So right, the balloon is being inflated. As the balloon's being inflated, it's growing. So this has to be positive. Is everybody okay that this is dv dt? Okay, so here's what they did. They said on this problem, even if you just wrote that down, you did nothing else, 1 point.
Perfect.
Like, for real. You were like, you read this, you did something good. What else do we know? Stephen, you're frozen. Any other important stuff? Polynomial is still frozen. Celeste.
the volume of the balloon is 144 pi cubic centimeters?
Okay, so the volume of the balloon is 144 pi cubic centimeters. Always?
No,
There's like this instant in time, right? Balloon is getting blown up, being inflated. There's an instant in time when this is true. Aaron, what you got?
And the radius equals 3 centimeters.
And the radius is equal to 3 centimeters. I don't think they were awarding any points for that because that's not calculus, but over here, converting over to rates counts for something. Now the tough part, what's the constraint? What's the formula that brings everything together? This winds up being geometry knowledge, not calculus knowledge, and this one they're just being mean. Celeste, what you got?
the volume equals pi r squared times 8.
Okay, the volume is equal to pi r squared times h. That formula gives you volume for the cylinder.
Plus
And now we've got to add stuff. Lewis, what are we going to add on here?
the area of the circle, which is
The area of a circle.
the volume of the
Volume of a
Here.
sphere. Hemisphere, half a sphere. Another half of the sphere, put them together. Got a sphere. Volume of a sphere. Anybody got it?
403 pi.
4/3.
Wait, yeah.
There's a 4 and there's a 3.
4/3 times pi pi
There's even a pi.
r squared.
There's an r, and because it's volume,
Pi r cubed.
it's better be cubed. I would not expect anyone to have that memorized. I am not worried about that knowledge. Okay, I would give that to you, and so will the College Board now. Apparently they've lowered the expectation since 1985. So that's the volume of a cylinder. All right, let's see. At this instant, what's the height of the cylinder? Not dh dt, what's h? All we're going to do is we're going to plug in. Okay, so I'm going to do that part really quickly because I'm not as interested, so feel free to go as fast as you can here. Volume is 144 pi. Pi, my radius is 3 squared times h. 4/3 times pi times 3 cubed. What is this? 144 pi. 9 pi h, that's 27. Divided by 3 is 9.
36.
Plus 36. Subtract the 36 pi. 108 pi equals 9 pi h. We're going to divide both sides by 9 pi. 108 pi divided by 9 pi. The pi's cancel. 108 divided by 9 is 12. So the height is 12 centimeters. Now, I think they are being really kind to you at this point because they've just asked you a question that has nothing to do with calculus. I think what they're doing is they're setting us up to be able to move into this next problem and have all the information. Okay, so now here's the thing I'm really interested in. D, at this instant, how fast is the height of the cylinder increasing? You guys know exactly what I'm asking for here. How fast is the height of the cylinder increasing? I need dh dt, so we have to figure out how am I going to get dh dt, and we may not have enough time to finish the whole thing. David, what are we going to do? How are we going to go about finding dh dt? we're gonna find the derivative, okay? I would say it's a 2-point derivative problem. If you can correctly find the derivative of that constraint equation, 2 points. And I bet for most of you, once you find the derivative, you're there. Because we're just gonna plug stuff in. Yeah, so I'm gonna do it. Don't look up until you're ready. So dv/dt, pi is a constant. I'm just going to ignore it for now. I see that I need to do a product rule. I am not ready to apply the product rule yet. I'm just going to leave myself a little note. Hey, go take the derivative with respect to t of r squared h. Derivative of 4/3 pi r cubed, 4/3 times pi times 3r squared times dr dt. So if you've got that part right, 1 point. Derivative of r squared h with respect to time, 2r dr dt times h, plus r squared times dh dt. If you get that part right, that's probably where the second point's coming from. How many guys are in the first point? Or maybe you wrote it as 4 pi r squared times dr dt?
What if you just wrote like the last one? Do you have to do all of that? Because I just did the last one.
Wait, you went straight to here?
Yeah.
Great, that's fine. I just did this so that like folks who are like tracking along with this are like, all right, I see what you did. Pi times the derivative over here, but I didn't take the derivative yet. Derivative stuff over here. And then I simplified. Okay, so yeah.
Where does the h go in the last one?
Where does the h go in the last one?
Because the one above it says dr dt times h.
2 pi r dr dt. Where'd it go? It's there.
Sorry.
Your It was one of those moments, Celeste, I felt something was wrong, and I'm like, yeah, they'll figure it out. Is everybody okay getting here? So the last thing we need, what's dh dt? And let's just run through this. Do we know all the things that we need to know?
Yes.
We've got dv dt. 2 pi, do we know the r?
Yes.
R is 3, do we know dr dt?
Yes.
Thank God. We figured out h, like this was the thing coming into this problem you didn't know. And if that situation were to come up tomorrow or on the unit test, you're going to go back to your constraints to figure out the h. So you figure out the h, you get r, you know pi, 4, pi, blah. Hopefully you're going to come up with dh dt. Okay. In just a little bit, I'm going to email you guys solutions in Southwest and East End as well. Solutions to the multiple choice and the free response. Strongly recommend you spend an hour or so studying, practicing those problems before the unit test. Unit test is due Friday. Stay away from boys. Boys are bad. Say no to drugs. And send money.